Welcome to our third video on describing continuous distributions. And in this particular video, we're going to talk about how to actually quantify the location. Remember when I said for a distribution, we look at its shape, where it's centered, or we could say where it's located on whatever scale it's measured on, and we're going to look at spread. So we're going to start looking at ways of using numbers, which we often call statistics, to actually assign values to the centering and to the spread. So I'm going to begin by talking about measures of centering. So I'm going to go ahead and go on to Slideshow. Okay. And there are three general ways that let me get going here. Set up a pointer option. Okay. Two of these are actually, let me get this to work right. There. Okay. So we have two of these are really important. The mean and the median. Something called the mode, you'll see, is not used that much in statistics, although the concept is actually useful. So let's explain the idea of location. This is a simple experiment by engineers, and they're bonding wires from a socket to a microchip for use in an electronic device. So they select 8 bonds and they measure the force required to pull them apart. So here are our 8 measurements, and by the way, this is called a dot plot. We don't really do much with them. Sometimes they're useful for visualizing very small amounts of data. So how would we describe the distribution? Well, it seems to be centered at 13. Just looking at it, and it seems to run from about 12 1/4 up to about 13 3/4. And with 8 observations, I really can't say much about centering. Okay. Well, probably the most common way we measure the location of a distribution, that is where it's centered, is the sample average or sample mean. And everyone knows how to calculate an average. And there's a notation often used in statistics. We often use a symbol to represent some variable we're measuring. So here we're using x. If we put a bar over the symbol, that says this is an average. It's not a single measurement. And in fact, you'll see later in quality control, averages are often just referred to as X bar. In fact, some people, I doubt if they even know where the term comes from. So it's just the average. And this may seem a little subtle, but the average is like the center of gravity or balancing point of a distribution. It is not necessarily the middle value, that is, half the observations are less than the mean, half are greater. In fact, that's often not true at all. So if we thought of our dot plot with our measurements on it as a balance beam, the average is where you would put the fulcrum so the beam is balanced. Okay? That happens to be 13. Okay? So that's the sample average, and that is a measure of where the distribution is located. Okay. Well, the second most common way we measure where the location is centered or located, we can use both terms, is called the sample median. The median is always the 50th percentile. That means, unlike the mean, the median is always centered in the distribution, so half the observations are less than the median, half are greater. Okay. So if a distribution is symmetric, so if it's symmetric, then the sample mean and the sample median are about the same. If the distribution has a long right tail or left tail, then typically they're very different. Because remember, the average is like the center of gravity. So if you have a long right tail, the average will be pulled towards that tail in order to balance the distribution. Likewise, if it had a long left tail, the mean would be pulled to the left by that tail. But the median is unaffected. It's simply the middle value. Okay. So here's an example. This is that delivery times data we introduced in the histograms video, our first one. And notice the average time to ship a product is 9.21 days, but the median is only 6 days. Interesting, isn't it? So what this is saying is 50% of the orders are shipped within 6 days, 50% are shipped later. The average has no such interpretation, and the average is greater than the median because we have a long right tail. Okay. So for skewed distributions, in point of fact, I think the median is a better measure of centering for the distribution. In other words, I think saying the average is 9 is a bit misleading because in reality 50% are being shipped within 6 days. So in dealing with strongly skewed right or left skewed distributions, I really think the average or mean gets overused, and we'd be better off using the median, and you'll see that will be our practice during the course. So from this we can say the distribution of delivery times are centered at about 6 days. Okay. Now let's look at the aluminum lithium data, okay, where the distribution is symmetric and mound shaped. So on average we're at 162.66 KSI, but notice the median is almost exactly the same. Why? Because both tails are approximately the same shape. Okay? In other words, they're symmetrically distributed about the mean. So the 50th percentile, the median, and the mean should be very close, and they are. So for a symmetric distribution, there are a lot of reasons why the average is a better way to describe where the distribution is centered. It turns out for some statistical methods we'll use later on, the mean is actually a little easier to use. Okay. And the mode, again, the mode is the most frequently occurring value in a data set, but since these are continuous distributions, there are actually infinite ranges of possible values, so the mode isn't really all that important. What's key is basically thinking of the mode as a peak. So the aluminum, lithium, and delivery times data were unimodal. They had one peak. Bimodal, we actually showed an example of this in the early notes, is bimodal, okay, in the understanding variation section. And multimodal means there could be multiple peaks. Again, if you're seeing more than one peak, this tends to indicate you've got distributions mixed together. In other words, somewhere there is a variable or set of variables that really separate these two distributions. They're not the same. And somehow in your data you've gotten them mixed together. So I'm going to give an example. This is from a project I did a number of years ago with a company that makes asphalt and paves roads. And that's what they do. And I had several hundred measures of the asphalt content in each batch that they make. And in theory, all batches are made with the same recipe. They should all have the same percent or proportion of asphalt content. So I did a histogram, and what it showed is, notice, it looks like there's 4 different distributions here. we would call this multimodal. Well, this says to me there's somewhere there's another variable or variables that are involved that means or defining separate distributions, and we've gotten them mixed together. Well, it turned out we found what that variable was. They actually have 4 batch plants where they make the asphalt, and the data came from all 4 of them. Now, in theory, all of them were supposed to be centered at about 6%. I think that was the target. So notice one plant is pretty close, although notice they did have an outlying batch, and by the way, that is a problem right there. That would be a quality control issue. One plant is centered at 8, okay, another roughly around 5.5, and yet another one around roughly 7.5. And by the way, these are considered big differences. These aren't trivial. The point is, it now was obvious the 4 batch plants were not all operating the same way, and now a team had to go in and figure out what was going on, because again, 6 was actually the target, and only one of the plants was really hitting the target. Actually 1 and 4 weren't too bad, but 7 and 8 were too high. And by the way, too high means the asphalt will be too soft and it will not have a very long lifetime. Okay, 6 was what they were targeting. Okay, so I'm going to make this a short video, and in the next section we're going to talk about how we measure the spread of the distribution, or scatter.